A battery dies because we don't merely borrow the voltage of a battery, the potential of a battery. Instead, we choose to convert its potential into current, and thus we drain it of its voltage by conversion of its voltage or its potential into current, and we use the current. And in order to use the current, we have to send it back to the battery. Of course, we don't put a reactive circuit in between to recycle the current on top of the problem, but the solution is not to spend the current. Now, capacitors are a very interesting thing. When they're small, value of capacitance, they cannot get rid of their charge fast enough. You give them a charge at one rate, meaning the rate of current that's feeding a capacitor, and it sends the charge back to you by discharging itself faster than it can get charged. A big value capacitor is the opposite. You keep feeding it current, and it doesn't want to let go of the charge that builds up within itself, resulting from the current that you send it. So its discharge rate is less. Like a 10 farad capacitor, its discharge rate is less than its charge rate. But a small little picofarad capacitor is discharging faster than it charges. And the end result is if you put a small 1 picofarad capacitor adjacent or in line, in series with a battery, what happens is you've blocked current from leaving the battery. In other words, it's going to bounce off that capacitor and be sent back to the battery faster than the capacitor received it from the battery. So you end up getting a slight trickle charge resulting or coming back to the battery. And you haven't spent its current. You've simply borrowed its voltage. That's the only thing. It's like a filter, like a prism. A capacitor is like a prism in that it filters. And if you put it in line with a battery, it allows the voltage to go through, so you still get the 1.5 volts or whatever it is the battery is offering you. You don't get the current because you send it back faster than the battery can give it to you. Talk about the recycling of energy. You're recycling current. You're sending it back. Now, this is a situation that has to be in which the capacitor is not a load. It's simply used as a reflector to bounce the current back to the battery faster than the battery can lose it. And the battery ends up getting a trickle charge and never goes dry. But you don't get the benefit of the current because you're not trying to. All you're trying to do, if you're smart, is to get the benefit of the voltage potential that the battery has to offer you, because that's what the battery is. It's a voltage source. If you choose to get your current from somewhere else, you will have that battery as your voltage friend for the life of the battery, and you will never have to recharge the battery because you never spend it. This is the value of so we don't worry about what Tom Bearden would say, don't kill the dipole. We simply don't use it. And if you don't use it, see, a dipole means current. In order to spend current, you have to take it from one leg, from one terminal of the battery, and send it back to the other. But if you send it back to the terminal that sent it to you, then you never send it back to the other. So in a sense, we're taking Tom Bearden seriously. We don't kill the dipole because we don't return the current to the opposite terminal. We return it to the same terminal that it came from. And I'm not going to get into which terminal because it's so confusing, that argument. Whichever terminal of the battery, the positive terminal or the negative terminal, sends out current, we send it back saying, no thank you, I'm okay. No, I'm good. You know, somebody says, you know, they're satisfied, they don't need your help, thank you very much. That's exactly what we do. Yet, despite us saying that, we still get something out of it. We get the voltage. We get to use the voltage. Now, voltage is not something you can use. It's like an ambiance. current is what we use. How can I say this? A potential. Well, see, now that's why Eric Dollard keeps correcting people. It's the way to describe what a battery has to offer insofar as its voltage is concerned is a potential difference between the two terminals. And that's literally a potential for current. And our mistake is converting that potential into an actuality of current, which kills the battery. Now here we have an example of how to go about getting current from another source and merely use the battery for its potential and never spend the battery. So we've got a battery, actually we have two batteries sandwiching on either side of a 10 microfarad capacitor. So the batteries are 1 microvolt each. So they're dead batteries. And the capacitor in between them is blocking their ability to give up their charge, their potential as a conversion into current. And then we use parametric variation of a capacitor varying between 10 millifarads and 10 farads, so a difference of 1,000 to 1 in terms of capacitance, and also a high enough capacitance, not something meager, so that capacitor can actually store a charge because it's big enough to store it. And we oscillate it through a coil of 2 henries, and we have 2 of them to alternate between. So every time we switch to a different coil, the capacitor changes to a different capacitance. And in so doing, we can't help but build up more and more voltage and more current in the circuit. It just keeps going up and up and up. Meanwhile, in order to charge this thing, to get it to run in the first place, the amount of energy we gave the circuit is a mere 20 nanoamps to get it going. So we didn't lose a whole lot of current from that battery. And in fact, we didn't lose anything because it's exactly the same, both positive and negative, because of that capacitor. Capacitors are oscillatory objects. They oscillate current because they receive current and they send it back. So that creates oscillation. It's a bouncing effect, kind of like bouncing a rubber ball off a wall. Only in this case, we take a bowling ball and bounce it off a rubber wall, and that capacitor is serving as a rubber wall. Actually, it's not a small level capacitor. It's kind of in between, intermediate. And I just picked a figure, 10 microfarads. But we use the battery to get the circuit going, and so the amperage coming out of the batteries is exactly the same in this instance as what's returning. I can't find an instance right off the top of my head that sends it back slightly to the battery. The current is sent back slightly more than what it discharges, but in this case it actually sends out, in this case, 36.68, no, 34 point, I can't stop this thing fast enough, 30.08 nanoamps versus negative 30.08 nanoamps. So that was just one example. You'll probably get other examples of your own. And actually, oh, I see what's happening. So I forgot. Working any switch in the circuit changes the parametric variation of the capacitor. That's the way the circuit is designed. And the battery has its own switch, and so every time you run the switch off the battery drains and is recharged. So now we get to not only beef up the energy of the circuit, but we get to charge the battery with a larger amount of current. And yet it didn't cost us anything because we're sending it right back to the battery. Isn't that beautiful? Now this is all theoretical, and I don't even know if you could build this thing, but it certainly exhibits an example of how to properly use batteries and not waste them. Okay.